Hello. Let's look at diffusion through a varying cross-sectional area. All along, we're looking at constant area, but now let's look at how to solve scenarios where we have our cross-sectional area varying. So, in such situations, we want to define our molecular diffusion and flux. Na is Na bar over A, and we take note that Na will be constant, but A is varying is on that one. So let's look at a scenario where we are looking at diffusion from a sphere. So let's consider diffusion to or from a sphere in a gas. So this particular situation often appears in cases as evaporation of a drop of liquid, evaporation of a ball of naphthalene, diffusion of nutrients to a spherical like microorganism in a liquid. Right, so Fig 1.34 that you will see later. So this is Fig 1.3 where we have got our sphere there and indicating our movement of the liquid and how the cross-sectional area is changing. So a fixed radius Ri m in an infinite gas medium, component A at partial pressure Pa1 at the surface is diffusing into the surrounding stagnant medium, where Pa2 is equals to 0 at some large distance away. So if we are to assume steady state diffusion there, we want to see how to make use of this. So this one is diffusion from a sphere. Then B is through a circular conduit that is tapered uniformly. Right, so flux Na can be represented by equation 1.323, where A is the cross-sectional area 4 pi r squared at point r distance from the center of the sphere. So this is our equation 4, 1.324. So this is the equation we are talking about as representing our molar flux. So this flux, it means it's changing with respect to the distance r from the sphere. So this is a case of A diffusing through stagnant non-diffusing B, and we make use of this equation Na1 minus PAP is equals to GABRT. So this is the equation. This equation is what would you have to substitute for this Na. Then we see how to then integrate that. Right, so this is the equation we have and our distance there, instead of dz there, we make use of r. So, as I have already indicated, the dr was substituted for dz, then rearranging and integrating between r1 and some point r2, a large distance away. This is showing our integration. Then after integrating, we've got our equation 1.328. We've already applied the limits in that equation. Then noting that PB is equal to the equation given as 1.329. And if since R2 is far much greater than R1, you'd find that 1 over R2 is approximately equal to 0. Then we substitute for PB, uh, PB log mean, as indicated there. We would find that we get equation 1.33 knots. So this is the equation we will use to calculate flux through a change in area. So the equation can be simplified further if PA is small compared to P, that's a dilute gas phase. Also setting R to R1 is equals to D1, which is the diameter, and CAU is equals to PA. So this is the simplification we obtain there. So this same equation can also be used for liquids where GIB is the diffusivity of A. So if we now look at diffusion through a conjugate of non-uniform cross-sectional area, as indicated there, where we are saying component A is diffusing at a steady state through a circular conjugate which is tapered uniformly, is shown in Fig 1.34b. At point 1, the radius is R1, and at point 2, it is R2 at position Z in the conjugate. So going back again to our equation as indicated is there, we would now need to solve this let's convert this into the differential form and integrate it. Right. So using the geometry shown, the variable radius can be related to position Z in the path as follows. So we have created a relationship between Z and R there is indicated. So diffusion through a varying cross-sectional area. So we first substitute for R, so as to eliminate R, then, and the equation is integrated as indicated there.